word to the formal abstract session. Jesse, take it away.
Thank you, Jeremy. Okay, everyone. Thanks for coming to the formal abstract session. I am pleased to introduce my fellow PhD student, Berlioz, who will be talking about text mining the archive.
Hello, everybody. Thank you for being here. So I'm going to tell you about this machine learning system that we're building for the formal abstract project that is able to detect definitions in mathematical literature, especially math articles from the archive. So the task breaks up very naturally in two parts. The first one is a classification problem, and so given a paragraph in a mathematical article, tell whether it looks like a definition or it doesn't, right? And the second one is a name entity recognition system, which detects the term being defined in definition. So for each of the two tasks, I will describe how we're able to get and process the data that we're using and train the machine learning system and take a look at the results that we're seeing. So the first part is to get loads of mathematical text. So you can download the whole archive from this website. It's actually an Amazon S3 bucket. So the Amazon is about 1 terabyte of this large tar file, and it contains the PDFs and the LaTeX source. So,
Actually, Luis, I'll do the same thing that I did before. So with the Zoom and the recording, you basically get to the end of the podium. So if you, yeah, perfect.
So, so we download it from here just to not affect the archive website traffic. So then we have all this LaTeX source, right? And LaTeX is kind of tricky to work with. So we need to convert it into a more structured format, which in our case is XML. So we use LaTeX ML, which is a LaTeX to XML converter. It works very nice. It's written in Perl by Bruce Miller. And it's a pretty stable and mature project already. So it works fine with us. We have tried several other things, but this is the software that we keep hearing. So
Did you try plastic? This looks much more suitable for this.
Yeah, we have so plastic is like the Python alternative, right? Yeah. So plastic works really well, but it's actually hard to get help with it. I think because we don't know the developers, and we know Bruce Miller, the developer of LaTeX ML. Yeah, so that's kind of the only reason why we haven't actually used plastic yet.
I mean,
Plastic is an alternative software that does the same thing, and it's written in Python.
I mean, in the disclaimer, I'm currently one of the maintainers of plastic. So but I'm not at all the original author. I mean, the original author is indeed doing other things now, but I took over maintenance. I can still answer questions.
Thanks for telling that. Yeah, I didn't know that.
But you don't even ask any question on the GitHub page of plastic, did you?
We kind of, most of our questions were directed to the Stacks project and the Derby team, because they use it to do the Stacks processes the LaTeX files with plastic. But yeah, that's about it. Okay. So moving on. Okay, so how do we get our the examples for the classifier, right? So we So sometimes the author of an article tells us that something is a definition by labeling it, right? So in the LaTeX, they would put something that tells us that it's a definition. And so this is how a labeled definition looks like in the XML output that we get. So to get examples of non-definition, we just sample random paragraphs out of paper, and we assume that they are not a definition. Of course, there's a problem with that, but we just tolerate it because we haven't thought of anything else to do. So we think it's worth it because, so for example, we're getting much more non-labeled definitions that we wouldn't get if we didn't use the classifier. So for example, from the 2015 algebraic geometry paper, there's 1,700 papers in that year of algebraic geometry. So there are a little over 5,000 labeled definitions, but we can find 71,000 probable. So we really want to find them all. So we like it. So some results of the classification. So the numbers are decent, and here we see a few examples just to see that the classifier is not doing anything crazy. And here we see a histogram of the distribution of how the definitions appear relatively on a paper, right? So, you know, there's maybe the abstract, there's a lot, then decreases and then decreases a little bit. So that's how it looks like. Okay, so that's it for the classifier. Now we are going to do the name entity recognition. So in order to train the name entity recognition, we need a definiendum and definition pair, right? So the way we find those is that, for example, in the Wikipedia data set, we go through all the articles in the Wikipedia and looking for articles that have a section called definition, and which and the title of that article appears in the definition section, right? So, for example, this is a real example. Definition section, and there's the title of the article. So there are very few matches for this criteria. So, for example, out of the 6 million articles in Wikipedia, we could only find a little over 5,000 matches. So we have covered some other websites also. We can deal with any wiki type data set, like for example the approved wiki and group prop pages. So we can find a little over 500 examples from that. The tax project has about 3,000 definitions that we can work with. And the Planet Math, recently we just started to see how it works. I think we can find 1,500 projects from that. So yeah, so there's, I think we have enough examples to train the classifier. So
have you tried the NLab?
No. Yeah, we haven't tried it. Yeah, it's a good.
You might find that the definition of group on the NLab is some kind of infinity. It might differ from the definition on Wikipedia. That's what I'm saying.
I mean, the NLab is a great source because it's only definitions. There is no theorem.
So yeah, the NLab we haven't tried yet. So this is how the name entity recognition system works. So we use an IOV parser, and it's just an off-the-shelf routine in the NLTK library. It's a Python library for natural language. So IOV stands for Inside outside and digging. Sometimes they call it bio. I prefer bio. So the input for this system, to train the system, is a list of words that make up a sentence, right? The part of speech of each word that you can find automatically. And it outputs O if it's not part of the term being defined, and if, and D or I if it's inside a definition. So we're getting those results. They're not great, but I think we think we can make it much better using more modern techniques and something like that. So these are some results that we're looking at with name entity recognition. So there are things we really like about the results. For example, if when fed this sentence, right, it detects the whole term, right? That would be the term that I would pick as the term being defined. Some things we don't like is that it pretty much picks every technical looking term that it finds, especially when they're short sentences. So we can deal with that in several ways. For example, we can just omit repeated terms. So for example, this is a cumulative curve of the number of terms that are being found in the algebraic geometry 2015. We use algebraic geometry a lot just because alphabetically it's the first one that shows up. So this is a number, so we can see that it's pretty consistent in the terms that it's finding. And we like the results so far. So some conclusions. So we think that we have something that we can actually just need to do a little improvement, and we can have a system that actually does what we want it to do. And after that, essentially we want to run it through the whole archive or every mathematical literature that we can find, and just do a really big comprehensive glossary of mathematical terms, and then we can organize it. The most natural organization is a dependency tree. We think that that would be helpful for formalization projects and maybe for the formal abstract project in the future. If we can visualize it nicely, it can be, something that people would browse or something. After that, we can actually create word embeddings. If you guys know what that means. So a word embedding normally just breaks up the term as the tokens that it appears on the literature. But we can actually create a new token that actually makes natural mathematical terms similar to each other. So for example, it would break up Banach's space, but it would work as one token, the whole thing. So there's a lot of work to be done in the disambiguation of the same term in different areas, and there's a lot of stuff you can do about that. We can just apply standard techniques and natural language technology. So that's it for me. Thank you very much.
We have a few minutes for questions, if anyone has a question.
What is the number of your non-definition, like the number of non-definition central in comparison with the definition central?
So for a classifier, it's best if the number of examples and non-examples are balanced. So we try to keep it 50-50. Yeah.
And also, between non-determinism that is predicted as a definition and a definition is predicted as a non-determinism, which is worse. Like, do you give more penalty to one than the other, or
Yeah, we have tweaked a lot of stuff. There's not like a natural thing that we prefer false positives or false negatives. We don't really have a clear preference there. So we just tweaked it.
so we is the same?
Mhm.
Do we have any more questions? Yes?
I just wonder, how do you deal with possible multiple definitions with a single paragraph? You mentioned that learning task is that you give a paragraph whether it's definition or not, but if you ask several, yeah?
Yeah, but in the example we saw, there were two definitions in the example that you liked, and you found only one.
So this one, what do you mean?
Yeah, I mean, you didn't pick canonical generalized scalar structure as a definition, the second sentence.
Oh, yeah, that's, this is the one that is picked up. Yeah, the second one it didn't. Missed that.
That's an instance of this question.
So is that, so your question was that, did that answer your question?
Yeah, to understand, basically this question about setting of the problems. The problem is given an abstract, or given a paragraph, whether it's definition or not. Probably it could be extended, given a paragraph, whether there is a definition or how many of the definitions is there.
Right, yeah. So
Or
we
maybe
can,
not to split it in paragraphs, just to fragments of the text.
yes.
And then
Mhm. Yeah, right. So we can we can do a little bit on that by just splitting into sentences or just eating the whole thing and just tell it to find just one definition. We tried that in all our examples. There's only one definition, there's only one term being defined in all our examples. That's what we have tried with our data sets, but yeah, there's other ways of doing it.
So we have time for one last question. Neil?
I think this LaTeX file you got in the archive, it's a very rich structured data set. You could look at, for example, they all come tagged with a mathematics subject classification. And then if you've got definitions, then you can map out explicit references to definitions. Have you had any kind of thoughts about giving any more of this?
I agree. We definitely need the first data set, and then there's so much to play around with. Yeah, it's a really, there's a lot of stuff to do. We also would like to, so we cannot actually give you the process, like we cannot distribute the process archive because we don't have the copyright of that, but we can actually distribute the software that, so you can download it yourself and so that's in our plan.
Also, have you tried to compare your list of definitions with things that are actually defined in any of the standard jurisprudence?
Yeah, so that's one of the things that we are really looking forward to. But actually, probably the archive would not be a good place to do that because maybe there's the perfect choice project, but that would be an exception. Normally, like Wikipedia would be or Planet Math would be a much better place to look for. Yeah, we actually want to do some alignment. There's a little bit of research done with aligning dependency trees between different prover libraries. For example, the Mizar and the Isabelle libraries. We want to do it we want to try it out with natural language and Mathlib or yeah. So we would like to try that.
Have you had any contact with Wikipedians?
Well, I know a few actually, but no, I haven't done with the project yet. They pack it in a way that's so perfect for research. I think it's a pretty common data set nowadays. Yeah. It's like perfect. You can actually analyze the whole thing on your laptop.
I mean, yeah, I think our community could benefit from talking to people.
Well, you're a little bit over schedule, so we'll have to take the rest of the questions offline. Feel free to whisper amongst yourselves during my time. But that was a very exciting note to end on, so let's thank Luis again.